Okay, good morning students. Today let us see one more trick in this problem. Here is a wedge given here. A block is sliding down the wedge. The wedge is of course fixed. It's not moving. And the lower half of the incline is rough and the upper half is smooth. The upper half is smooth. Okay, right. Lower half is rough and it's having a coefficient of friction mu. And in the question they have given that the block slides down and just comes to rest at the end of the wedge. So block, condition is given, block just comes to rest at the bottom. This is a very important point to be noted. The block just comes to rest. That means it is just coming down, it's speeding up here, slowing down, and it has come to rest on its own. It's not hitting the surface down. So automatically the velocity here has become 0. So there are two cases, no? The block can hit down or it has just come to rest on its own. That means the final velocity is 0. Initially it is starting from 0 velocity. Now this problem involves a lot of tedious process by calculating the velocity at this point first. I name it as A, B, C. I have to calculate the velocity here. Then it keeps on retarding here. Upward force mu mg cos theta is more than mg sin theta. Therefore net force is up and the velocity is downward. Hence it will retard. All these conditions you have to consider and the problem becomes very tedious, and you have to use the equations of motion also there. Now I will give you a small trick here. Actually it comes under the friction topic, but I can use work energy theorem. According to work energy theorem, work done by all the forces on the body equal to change in its kinetic energy. Again I am repeating, work done by all the forces on the body is equal to change in its kinetic energy. It means the body's kinetic energy. Now let us see. Work done formula is Fs cos theta. F into S into cos of the angle between F and S. In that way you remember. Don't remember it as cos theta. Theta will be changing depending on where F and S is. So you remember in this way. Force into displacement into cos of the angle between the force and displacement. Now let us see first of all what are the forces acting on the body. One is mg vertically down, no doubt. The other is of course normal reaction. Normal reaction is perpendicular to the surface always, and as it comes down, as long as it is sliding from A to B, there are only two forces on the body, that is mg and normal reaction. Once it enters the surface having friction, there is frictional force behind. Don't forget that. Of course N is there still, and of course mg is there. That means as long as it is on the smooth surface, there are two forces. Once it enters the rough surface, there are three forces along with the friction. Work done by all the forces equal to change in its kinetic energy. Now let us see one by one. Work done by mg, work done by normal reaction, work done by friction equal to change in its kinetic energy. Now mg is down, displacement is in this direction. Look at the arrow mark. Of course, look at this. mg is down, displacement. Look at this here carefully. Of course mg is throughout. I cannot say mg had disappeared. So mg into S is 2L into cos of the angle between mg and L. This is the cos of the angle. This angle is, if this is theta, this will be 90 minus theta. So what is the work? Let me write here. Work done by mg plus work done by normal reaction plus work done by friction equal to change in the kinetic energy. Here the final kinetic energy is 0. Initially is also 0. You are not pushing the block. So the change is 0. Final is 0. Initial is 0. The body has just come to rest. It's not hitting the ground. Okay. So the change in kinetic energy is 0. We are taking the motion from A to the end, that is C. So work done by mg. mg into displacement 2L into cos of the angle between them, cos of 90 minus theta, that is sin theta. So I have mg into 2L, mg, force into displacement into cos of 90 minus theta, that is sin theta, plus work done by normal reaction. Look at here. Normal reaction is perpendicular to the displacement throughout. So n into 2L into cos 90. Again, look at my diagram here. Look at the demonstration here. N into 2L into cos 90, 0. So work done by normal reaction is 0. Plus you have work done by friction. Now look at the chalk piece here. This chalk piece gives the friction force. This chalk piece gives the displacement. What is the friction force on the inclined plane as the block slides? Mu mg cos theta. Mu mg cos theta into the friction acts for the length of L only, not 2L. Very important. The friction is acting for the length L, not 2L. So mu mg cos theta into L into cos of the angle between friction and displacement, 180. Friction is this side, displacement down, angle is 180. So I can write mu mg, I am writing it here, mu mg cos theta into minus 1. I can write here minus 1 cos 180 equal to 0. The problem is solved. Once again, mg into 2L into sin theta, force into displacement into cos of the angle between them. Cos of 90 minus theta is sin theta. Work done by normal reaction is 0 plus work done by friction is mu mg cos theta into displacement is L. I can write here L. Mu mg cos theta into L, force into displacement into cos 180 minus 1. So I can write 2L mg sin theta equal to mu mgl cos theta. You can check there. I can bring this term this side. So mgl gets cancelled there. Mu equal to 2 tan theta. So we got the answer for coefficient of friction. Once again I am repeating here. Work done by mg. mg into s is 2L into cos of the angle between them. That's why I am using the word cos of the angle between them. I am not saying cos theta always. Cos of the angle between them. Cos of 90 minus theta sin theta. Work done by normal reaction is always 0 because the normal reaction is always perpendicular to the displacement. And work done by friction. Frictional force on the inclined plane as it moves, as the block moves, mu mg cos theta into displacement is L, not 2L, into cos of the angle between friction and displacement is 180. So cos 180 is minus 1. Simplify. That's equal to 0. Why? Change in kinetic energy. Final kinetic energy minus initial kinetic energy. So from this, if you simplify, you get mu equal to 2 tan theta. One step, only one equation, the problem is solved. If I take the problem in the other way to find out the velocity here, then it enters the frictional surface, retarding. Mu mg cos theta is more than mg sin theta. Then net force by mass is retardation. Then again I have to use v square minus u square equal to 2as. And you should understand that mu mg cos theta is more than mg sin theta. All these things requires more thinking. But here, very clear, I used work energy theorem instead of all that. That means what is understood here is in physics, certain problems we can link other concepts to make it easier. This is a wonderful trick. We can come back with some more tricks. Goodbye.